Okay. Let's. I think we can. Can you hear me, or is this? Okay, good. Let me move this a little differently. Okay. Let's get started. The homework one is due today. I'd like it done at the beginning of class. It should be done at the beginning of class. So in a minute, I'm going to go and dump my coat over these things. So if you have your assignment, bring it in now. Any questions about the homework? Okay. We're going to, let me go cover this up and say, boom. No more homework. Okay, well, put it in. Go, but last one. Okay. Any questions about the homework or anything else that people want to talk about now? Yes? Is it possible to go over question 311? I think I would rather go over the homework after you guys get it back. Okay, and so I think it's a week from today. You should demand it back. Okay, and hopefully you'll get it back. And if not, I will promise. You ask me that question then, and then we will go over it. Yes, question. We're going to post solutions. We are going to post solutions. Okay, that is the plan. When presumably, we are going to post it in a week. Okay, again, in principle, people can turn things in up to a week late. So it is good not to post the solutions before then. Okay, so that is my thinking on the solutions. Any questions? So in the meantime, once you've done this, I encourage you to, for the moment, forget it. Then you can start thinking about the problems on the second homework, which have to do with things like sorting. Because that is going to be on the midterm, which is, I gather, a week and a class from now, if I remember correct. Any questions? Okay, so let's talk about the daily problem, which is an interesting one about data, about, all these kind of things about data structures and sorting and searching and how things integrate. The question concerns that that you are given two sets of that you'd like to intersect. Let's say lists of names, okay? And you're trying to figure out whether they are disjoint, meaning that they don't have any intersections. Or I guess equivalently find all the intersections. So you're given a bunch of names. You've got Steve, you've got, Mary, you've got a total of n names here, and you've got another list of m names, okay, where n is potentially much, much bigger than m. Okay, so you've got a long list of people here, okay, and you've got a smaller list of people here, one of whom may be Steve, okay, and your goal is to try to figure out what the intersection of these two lists are. Any questions about it? Okay, now anybody turning their assignment in late, you are being filmed, so I know this, okay? Any questions? Okay? So how can we go? We have a list of names here, a list of names here. We want to find the intersection. How do we do it? Can anybody give me different proposals? Yes? Well, quicksort we haven't done in here, so in principle, maybe we can't do a quicksort, but by quicksort, what you're trying to say is we're going to sort which one? The larger one. One thing you can do is to sort the larger one. So you want to say, let's call this thing A and B, just for the sake of it. Your algorithm is sort A, then what are you going to do? Then you're going to do basically 4i equals from 1 to m. You want to search, do a binary search for a b sub I in A. That's what I hear you wanting to do. Am I correct? What is the running time of that algorithm? That running time is n log n to do the sorting of A, right? The running time of the second is going to be what? You're doing something m times, right? How much time is it going to take to do that search? Each search, yeah? Log n. That is going to be m times log m. Does everybody agree? No, it's going to be m times log n. Does everybody see that? Now, those are the two steps of the operation. What is the total time of this algorithm? Okay, one is n log m, and one is m log n. What is the big O running time of this? Yes? N log n. Why is it n log n? What happened to m? Because m is no bigger than n log n. We're dealing with big O upper bounds, right? The upper bound is this thing. This is what is driving it. This is bigger than this. So therefore, this gives us an n log n algorithm for solving this problem. Any questions about that? But is that the best we can do here? Okay, is there any other way to do this thing? Yes?
Using hash table every element.
Okay, so using a hash table in practice may be a good thing. What would happen if we used a hash table right? Let's say that the odds were in our favor and we used a hash table. What would this take? Okay, it would take order n time. You're going to build a big hash table of size order n, right? Okay, because order n plus m, which is really order n. You're going to hash them. You are going to hope that every element is going to get scattered. These elements will be scattered around nicely. If they are scattered around nicely, you will now walk over the hash table one by one, look at each bucket, and then look at the problem of identifying uniqueness in that each bucket, right? Now here we have in the ith bucket all the names from both lists that got hashed to the element I. Steve here is going to get hashed to the same bucket as Steve here, but it could very well be that somebody else might also get hashed to that same bucket. So your job is now to purify each bucket and look for are there really any duplicates within each bucket? How are you going to resolve the collisions within each bucket? What are you going to do?
My suggestion is would be when we insert putting the element, we can check.
Okay, so one possibility is when you insert an element you look in, but recognize you still have the same problem. So now you're going to, when you insert this element into the hash table, it's going to go to a bucket. You've got to search all the elements that are in that bucket. Does it match or does it not match? Right? So your time is going to be, for each element, it's going to take constant time to find what bucket it is. You are then going to spend linear time in the size of the number of elements in that bucket to see if there is a duplicate. And if everything works out right, there will not be too many things that got hashed to this. Checking for a duplicate is going to take constant time and everything is fine. But if you got unlucky, what's going to happen? Everybody got hashed to the same bucket, and you've accomplished nothing. Does everybody see that? So worst case, bad solution. In practice, not a bad solution. Okay? You shouldn't make it a business to use lousy hash table implementations, right? And so in practice, this is not an unreasonable use of hashing. But we're talking about worst case bounds, and so it is not what we're looking for today. Any questions? Yes?
Can we ever assume that we have a perfect hash function?
So there is such a thing. If you study the theory of hash functions, hashing more than I am, than we're talking about in here, there are such things as perfect hash functions. And a perfect hash function sounds perfect. Okay? What is a perfect hash function? In principle, for a set of keys, it is a hash function which will distinguish them, each element, to a unique element in the hash table. So then you know there's only one collision. There's no collisions. Okay? Now the trouble is you can't build a perfect hash function unless you analyze all the elements in advance. And this is fancy high-powered machinery, and it's not for a data structure-like thing. It's for a world where you know you're going to be making lots and lots of queries to this kind of a structure. And you want to make an absolutely fast thing for one you're willing to spend a lot of time pre-processing on. Okay? So for the purposes in this class, you don't know about perfect hash functions. In practice, perfect hash functions can be a useful thing. Okay? But it's, but again, it's something that is complicated to build. It only pays to do if you're looking for something where there's a relatively small number of unchanging things you're going to look for lots of times. That's when you might think about that kind of thing. Any questions? There is just, again, just to file it away, it should be clear now that there is this, this base of knowledge on building hashing that is big and messy, and there's a lot of interesting things you can do with it. Okay? In the worst case, they're all cheats, as far as we're concerned here. In practice, hashing is a good thing, and you should know about it. Any other questions about how you might do it? Yes?
When you hash the n out of the free hash b, then the worst case will be n.
Wait, so you're saying what you want to do is what? You want to hash the elements of b, okay? And now, what you're saying is you're still insisting on building a hash table. You want to build the hash table on the elements of B. Now, why would you like to, and then what you're going to do is look up the elements in A. Is it there? What's the advantage of building the table on B instead of A? The worst case of whether they're all in the same bucket is still true. But the maximum number of elements that can be in a bucket is m instead of n. So let's think what the worst case of his hashing algorithm is. He's going to hash all of these elements in order m time. Okay? He is then going to, for each of these n elements, do a search, which in the catastrophic case would take order m. Does everybody see that his worst case here is n searches of order m, right? Now that's not really any different than doing it where you built the hash table on this and searched here. Here you were doing n searches of order m. Before you were doing m searches of order n. Both of them would have been order nm in the worst case, right? Any questions about that? Yes? Now, however, this idea of switching what you're searching for and what you're sorting, or what you're processing on, does pay fruit, potentially, when you do the sorting different. What she is suggesting is that I sort B, okay? And now for I equals 1 to, what is it, n. Okay, before I had m, now I have n. Do a search for, what is it, a sub I in B. That's what I hear what you're doing. Am I correct? What is the time complexity of this one? How much time does it take to sort B? B here had m elements. This should be m log m. Is that right? How much is this algorithm going to take? This is going to be n log m. Am I correct? Because you're going to be doing n binary searches, each of which is in an array of order m. Right? What does this work out to? What is the big O of this plus this? Is it m log m plus n log m? Which is the bigger term? N log m. Does everybody see that? So this one is an n log m algorithm, whereas the previous way of doing it was an n log n algorithm. Which is better? Okay? Since n is much bigger than m, okay, this could be more expensive. Suppose we had a world where n was n and m was equal to 1. Let's say this was the number of people who were teaching the algorithms class you were taking, right? That would only be Steve, right? So then if m was 1, this would be reduced to order n, where you had here an n log n algorithm. Does everybody see that? So this is a better way to do it. Okay, this one is faster. Any questions? Yes? What? Well, to sort B here, this has m elements. M elements can be sorted in m log m time. Right? There's m elements. We're sorting it in m log m time. This thing has n elements. This takes n log n time. Because n, we said, is bigger than m, n log n must be bigger than m log m. Okay? It's 2 steps. There was the time to sort, which was here, plus the time to search. This was n log m. I'm doing n binary searches in a small m element array. Here, I was doing, I think, m binary searches in a big array. Okay? The bigger term here was the cost of sorting. In the other example, the bigger term is the cost of the searching. Okay? But the sum of the two is lower if we sort the small array first. Okay? How many people get that? Any questions here? This is interesting. Is there any other way? A question? Yes?
If we made no assumptions about how would we write the time perspective?
Okay, if you didn't know which way you were doing it, what you would probably be doing, what if I didn't tell you which was bigger? Okay? Well, what I would probably do, okay, so now how would I do this? What I would probably say is, okay, so that's a good question. Let's think about it. Let's think about it differently. A couple ways we could get around writing this. One way that would be true is if I notice that n plus m, okay, I could say the total amount of data in my thing is n plus m, and then write n plus m in everything that I do. Okay, and that would be one way of writing it. The usual way of writing it is to assume that one of them is bigger. Okay, because it's sort of just you can usually test easily which is bigger. Okay, if you think about it. Let's say I didn't care about it, okay? Oh, wait, let me start back, not get confused. The question is, suppose I didn't want to write it in terms of n and m. Is there a way that I could write it in terms of one variable? I'm given 2 arrays to sort, each of which is at most n. Then what would the algorithm be? It would be n log n, okay? Or this would be n log n. Right? Because you're not distinguishing between the arrays. It depends what you say you're being given. If I'm given 2 arrays, each of length at most n, it would be an n log n algorithm. Right? Here it is profitable to distinguish the relative sizes of the arrays. Because you can see that you can do something where one variant is in fact superior to the other. Does that answer what you're saying? Okay, so again, there are a couple things you might be asking. If I put this question on the test, which answer would be acceptable? Is it this or this? This is the one that deserves full credit. This is the one that deserves partial credit. Okay? The question of what parameters, what I think is maybe the more interesting question you're asking about, is when you're given a problem, what are the relevant parameters to describe the size of the problem? Okay? Usually people will say, I'm given two arrays of size n. Okay? And then my problem is order n. Here we saw that there was a difference if there was an asymmetrical, if one array was big relative to the other. And for that reason, it was worth specifying two parameters. I don't know if that helps you or not. Okay, any questions about that? Okay, is there any other way we could have done this, by the way? That we could have figured out the intersection of these two? Okay? Yeah?
Well, I can come up with something that isn't O and n squared, but still worse than what was on the board. We could concatenate the list B onto A and then sort the combined.
Okay, so what would happen? Let's just go through what the analysis thing is. Suppose, let's say we concatenated the list. Here's the n element list, here's the m element list. We said these guys came from list 1, these guys came from list 2. Okay, so maybe there's an extra field to show that they're distinguished, right? What he's saying is I can sort these things, right? Concatenate, sort, and sweep, and that would identify the duplication. Does everybody see that? So his algorithm is concatenate A and B, sort A and B, and then sweep to find, duplicates, right? Because they're going to be adjacent to each other after sorting, right? Yes? So this is assuming that the elements are, okay, so if I just say concatenate the files, sort, and sweep, you could get fooled if Steve happened to twice be in this list, right? That's what you're worried about. But if, on the other hand, I tagged all the things from the file A, I gave it an extra distinguishing secondary key of what the file name it was in, then once they were in a glop when sorted, the neighboring ones would be the same. Okay, so that's how I'm avoiding your problem. Any questions about that? So what would the complexity of this thing be? How much is it going to take to sort the concatenated file? Yeah?
N plus n log n plus m.
To sort it should be n plus m log n plus m.
Which is worse than
Well, what is that? Actually, say it's worse. Can anybody simplify big O-wise? What is n plus n log n plus m? Yeah? It's going to be n log n. Now, why is that? Let's take a look at this thing. Can we first argue? Let's look at this kind of carefully. I claim that this sum is going to be, this plus this is going to be less than 2n log of n plus m. Why is this? N plus m is clearly less than n plus n because n is smaller than it, right? M is smaller than n, right? So since this is less than this is going to be big O-wise, n times the log of that, right? Because multiplying it by a constant. Okay? So it should be no mystery that we can simplify this to being basically order n times this. And a similar argument would say that the log of n plus m is going to be less than the log of 2n, right? Which is going to be equal to log of n plus 1, right? Assuming you're doing a base 2 logarithm, right? So this is also order log n. So this thing itself can be simplified to n log n. Does everybody see that? Okay? Is that the complete algorithm, or is there anything else we still had to do that we didn't analyze? We didn't analyze the cost of the sweep, right? How much time is it going to take to go through that sorted list, looking at neighbors to see if they pair up? Yeah?
M plus n.
M plus n. Does everybody see that? It's now linear time in the size of the thing, which is n plus m. Right? So which is the dominant term? N plus m or n log n?
N log n.
N log n. Now, which is better? N log n or n log n or n log m? It should be clear that this thing is the same as the sort and sweep one, big O-Y's, right? But sorting the small one and doing the searching in the small one is the best option overall. Any questions about that? Okay? How many people get this? This is kind of interesting, because this is a level on which I think, there's some stuff in here that's complicated. This stuff is really, we're sorting and we're doing searching. Okay? You guys always complain, it's sorting too many times. Well, here is now why we sort. Okay? And you should be able to think about it like that. Any questions? Yes? Why does the search take n log m time? You mean over here? Okay, well, what are we doing in this code? First, we're sorting the smaller chunk. The smaller piece had m elements in it. It took m log m to sort it. Then what are we going to do? For every element in the big thing, we're going to do a binary search in the sorted thing. The sorted thing was order m. So one binary search took log m time. Does everybody see that the binary search, each binary search, took log m time? And how many of them are we going to be doing? We're going to have to search in this array here for every person in this list A, of whom there are n of them. So it's n searches, each of which takes log m time, n times log m. Any questions about that? Okay. Any questions about how you do this problem or what the logic here is? Okay. This is the kind of reasoning that we need to do to think about data structures and the operations and how you combine them. Any questions? Okay, good. Okay, so what I'd like to talk about now is, go through in some detail, basically today, about another data structure, that the priority queue or the heap, okay, in some sense, that among other things is used to speed up this selection sort algorithm, which I hinted at the end of class last time. What was selection sort? In selection sort, we were given an array. Okay, we wanted to sort it. What we did was make a sweep through the entire array, looking for the smallest element, swap that to the beginning. And now we have a sorted part of our array and an unsorted part of our array. In each of n iterations, we're going to find the smallest element in the unsorted part, and then pull it out of the unsorted part and put it at the back of the sorted part, okay, in order to sort things. So our algorithm was n steps of find the smallest and then pull that item out of the data structure, okay, the unsorted data structure, okay, and do it, okay. Any questions? So for an array, if we just use an unsorted array to represent the unsorted part, finding the smallest element in an n-element array took order n time. Pulling it out and moving it to the front took one step. This was became an n times n or n squared algorithm. That is the selection sort that you know and love from your first programming class. Any questions? But if we use a better data structure, specifically if we used a balanced binary search tree, we could find the minimum of the elements by just going ka-chunk, ka-chunk, ka-chunk down the left branch, okay? In time order log n, we could have found the min. We could have deleted the min, okay, in log n time. And so this could have been instead an n log n algorithm, where we make n iterations, we're finding the min took log n, and pulling it out of the array took log n. Okay, any questions? Yes? Okay, so you say the binary search tree means that it's sorted. I would say if it's in a binary search tree, that means that it's in a binary search tree. That's what I would say it means. Now, it is true that once you have a binary search tree, you can in fact read off the sorted algorithm order by doing an in-order traversal. Okay? I'm not using that property here. I'm just using the property that I can find the min in logarithmic time, and I can delete the min in logarithmic time. If I have a balanced binary search tree and all the glory I've said, I can do all of those operations in log n time. By using that for to do these two operations, okay? That gives me an implementation of selection sort that runs in n log n time. Any questions? Yeah. Well, okay. What's the point? What's the complaint?
You already have the element of binary search tree to just get sorted in all time.
Okay. So what you're saying is, if I was going to do, you're saying you don't like my version of selection tree sort, okay? And the reason you don't like it, if I want to understand it, is, first of all, to build the tree, okay, what you would have done is for I goes from 1 to n, insert in the tree. And that would have taken n log n time to do the initial building. And you're saying at that point, I insist on finding the min and deleting it. You want to shake me and say, just do it in order traversal, right? That's only going to take order n time. Okay? So this is an alternate way to get the same information. In a big O sense, is it different? Well, to build the binary search tree took n log n time, right? So n log n plus n log n is not better than n log n. So I'm not really worse in a big O sense building the tree and doing this selection sort using the balanced binary search tree operations, right? On the other hand, if you were working for me and you tried to pull a stunt like that, I'd say, why don't you do it in order traversal, right? Because, it seems like an easier solution, right? And it presumably isn't going to be slower. But the bigger thing you should be complaining about is, do I need this complicated machinery to build the balanced binary search tree? Building the tree, a balanced binary search tree, is so complicated a thing, that takes n log n time by itself. Maybe there is a lighter weight data structure that does these two things, okay? Without the mechanics of a balanced binary search tree. Balanced binary search trees are so complicated, I didn't tell you how to do it, right? I've told you you can do it. I've told you you can assume it. But if I asked you to program it, you would be unhappy people, right? So what I'd like to talk about today is a lighter weight data structure that is a useful thing that will give us the same bounds for this problem, and actually even better bounds in some sense than using the balanced binary search tree, okay? But the lesson that I want to make clear, if you want to say, what is the lesson of selection sort? The key lesson is, often, when you're using data structures, changing to a different data structure gives you a different mix of performance of these operations. And sometimes you can speed your whole algorithm just by changing the data structure so that it achieves the better mix for what you want to do. Okay, and that's something you've got to be aware of. Any questions? Okay, any questions about selection sort? Okay. So let me talk about here, sorry, bunk. Let me talk about another data structure that will let us do, we have to do two things here. We have to repeatedly find the minimum element, and we need to repeatedly delete it, the minimum element. These are the two things that we are doing in our selection sort, okay? So there is a data structure called a heap, which is a very interesting data structure that I'd like to talk about for today's class. A heap is a binary tree, okay? But it is not a binary search tree. Does anybody see the word search here? Okay, you do not see the word search, right? It says binary tree. A binary search tree is good for looking up elements, right? A heap is not going to be something you can look up elements in, particularly efficiently. But it is a tree-shaped structure where there is a key in each node, where the property of the keys are that the key for the root is less than it, than all of its children. And the right and left subtrees are again binary heaps. Meaning that the labeling, what this order is saying is that the labeling property is going to be wildly different than what we had on a binary search tree. Does everybody get that idea? This is not for looking things up. It's for efficiently finding the smallest element. And if we have a tree where this property holds, where is the smallest element in our tree going to be? The root. Okay, so how hard is it to find the smallest element in the tree? Constant time. It's there. Okay. So that is why this looks like a good thing for repeatedly finding the smallest element. Okay. The other aspects of the heap definition concern the shape of this tree. And a binary heap is going to have the property that not only is it balanced tree, it is a hyperbalanced tree. It is going to have a height of exactly log n, because all levels of this tree are going to be filled except the last one. And for good measure, we're even going to stuff all the leaves on the last one as leftmost possible as we can make it. Okay, let me show you a picture. Kabunk, kabunk. So here is a heap. This is a heap on a bunch of years that have come up in history, if you read history books. What is the property? It is shaped like a binary tree. All the leaf nodes are on successive levels. Every level above that is as full can be. Even the last level with the leaves is as full can be. And on the only unfull level, all the leaves are stuffed as leftmost as possible. That is the shape condition that I want my heap to have. Any questions? Now, in this one, the smallest year is the root. What is the second smallest year in this data structure? Which one is it? Then this, right? I guess we can maybe even write these out. This was the smallest. This was the second smallest. Where was the third smallest? Okay? In this case, it happened to be here. Okay? Okay? This happens to be the third. Where's the fourth smallest? I guess this was the fourth smallest. Where's the fifth smallest? It happens to be here. But note that there's no reason why the next smallest couldn't be either here, or here, or here, or here, or here. We are not demanding that these things be sorted. All we are demanding is that every node is the root, for every node, it is the smallest element in the tree subtree that it is the root of. Any questions about that? Okay? So do people see that there is this heap ordering property? Okay? There's a lot of flexibility in... When I told you about binary search trees, I told you there was one and only one way. If I gave you a particular binary tree with n nodes in it, and I gave you n keys, there was one and only one way you could label that tree. So it was a binary search tree. Remember that? With heaps, there is a lot more flexibility. The shape of the heap is completely fixed. But there are lots and lots of labelings for any set of keys that are going to be equally satisfying the heap property. Any questions? Does everybody agree I could have, for example, taken, let's say, what would be something I could have? What would be an alternate heap for this thing? Let's say I decided I wanted to have this node being labeled 1783. Okay? I could make the root of this thing be 1804, right? I could make what numbers do I still have? I could make the root of this be 1918, and the missing one I could put 1945 here. Does everybody see that this is an alternate heap of the same shape, okay, that still satisfies the heap property? Every year is still represented. Every node is still the youngest. This one is still the smallest numbered of all of its descendants. Okay? This property is still true for every node in the tree, but the labeling is quite different. Any questions about this heap property? Okay, yes?
That bottom right one is 1943?
This one is supposed to be 1945, which was there before. Okay?
And now it's currently 1943?
Wait, no, this was 1940. This is 1783. This is 1783 that used to be there. Okay. So writing, you can't expect me to write it. But anyway, it should be clear that there is an alternate arrangement, an alternate labeling for the same set of keys. Okay? Same shaped tree, same set of keys, different ordering, and it is still a legal heap. Any questions? Okay? So what really drives there's two different magic things about heaps. One is that because there is so much flexibility in the way you can label things, it's going to be very easy to build and insert things into heaps. Okay? The other thing is that because we have constrained the shape of the tree so tightly, the fact that we're going to be able to do things in heaps in order log n time should be absolutely no mystery. What is the height of this tree going to be? You say order of log n. It is exactly log n, okay? Which is order log n, okay?
Technically, it's CL log n.
So it's in this case it's log n plus or minus 1, okay? To be precise. Because, no, it makes a difference here. Why is that? Because there is one node on the first level, a total of 3 nodes after the second level, a total of 7 nodes after the third level, a total of 15 nodes after the fourth level. You can't build a heap that is larger than, if you have a heap of height h, it's got at most 2 to the h nodes in it, and at least 2 to the h minus 1. Okay, 2 to the h minus 1, half as many, right? Depending upon whether the last level is full or empty, right? So a heap is extremely balanced, and therefore anything you're going to do in it, okay, in principle, why it's going to be log n time, it should be pretty obvious. Any questions? Okay. So what can we do with a heap structure like this? How can we insert a new element into a heap? Suppose, let's say, we want to add an element to a heap. Oh, actually, let me talk about one other property of the heap before we get into this thing. There is also something interesting. Because the heap is so structured, we know exactly what its shape is. There is a particularly cute way that we can store this thing. To store a binary search tree, we described how to do that using pointers, right? We had nodes, they had left children, they had right children. Here, the shape of the heap is so tightly prescribed there's actually a way to represent it, okay, without actually explicitly storing pointers, okay? What we're going to do is store it where we're going to use the index of each element to describe where its parent and its children are, okay? In particular, we're going to use a numbering scheme where if we have a node that sits in the kth element, the element sits in the kth element of our array, we're going to represent it so its two children sit in the 2kth and 2k plus first spots in the array. Look at the example that I had on the previous slide. Okay, kabunk, kabunk. This array represents an encoding of this particular tree shape. How is it? We say that for the first element, okay, its children should be in the second and the third element in the array. 2 times 1 is 2. 2 times 1 plus 1 is 3. Does everybody see that according to that numbering rule? Okay? The two children of the root are in the right place. Any questions about that? Now, this element was in the second spot in the array. I claim that according to this numbering, its children are going to be in the 2 times 2 or 4th and 5th elements of the array. And that is absolutely right, right? This element is in the 3rd spot of its array. Where should its children be? 6th and 7th. And lo and behold, that's where they are. Does everybody see it? This element here is in the 4th spot of the array. Where should its children be? 8 and 9. This element is in the 5th spot in the array. Where should its children be? Its children are in the 5 times 2 or 10th, and it would have been 11th spot of the array, but we haven't filled it. Any questions? Does everybody see that there is actually a kind of slick correspondence where if you have a perfect binary tree, you could store it in an array without pointers here, okay? And the elements neatly fit, so there's no wasted space with this numbering. How many people see that? Any questions about that? Question like, I don't see it. Yes?
No, I mean, I see it. I was about to ask a problem. That might segue into the next.
Okay. First of all, any questions about this before we have any problems that will segue into something else? Okay, so now segue into something else.
All right. How are you going to basically reorder and reposition the elements once you have to insert something into the middle of your key?
Okay, so your concern, so what is good about this representation? What's really nice about this representation is I have stored my tree structure in some sense without wasting any space for pointers. That's what's good about this, right? You guys didn't like programming with pointers in the first place, right? And it took up space, okay? So it seems like this is great. I have no longer need pointers. Except, what is the problem? Pointers give you flexibility in how you can move things around. Your concern is, if this was a real pointer and I wanted to move this whole subtree, all I had to do was to basically change what pointed to it, right? Now to move this subtree, I would have to physically copy all of those elements around, right? So it should be clear this implicit representation is not going to be as flexible as pointers. Does everybody get that idea? It should be clear there are things you could do with the pointer representation you can't do with this. Okay? Any questions? The other thing that should be clear, if you think about it, is that this is going to be extremely wasteful. I mean, it sounds like a great idea. Could we represent any tree, binary tree? Again, I told you I had a particular shape of a binary tree. Could we represent any binary tree in an array? Could we represent this tree in an array using the same kind of encoding? The answer would be yes. This is element 1. Its children are going to lie at, this would be 2 and 3, right? This is element 3. Its children would lie at what? 6 and 7. This is element 7. Its children would lie at 14 and 15. We could represent any binary tree in this thing. What is wrong with representing this binary tree using an array? Okay, what is undesirable about it? Yes. It wastes space. Does everybody see my array is going to be a big array with very few meaningful elements? Okay? That's the downside of using this for anything that I can't absolutely guarantee is tight and balanced and beautiful. Okay? The size of the space that I'm going to be using is going to be basically, it's going to be exponential in the height of the tree. If my tree is high with very few nodes, this would be a horribly wasteful thing. Any questions about it? But if I can force my tree to be nicely packed, okay, then this is a good thing. And I'm going to be able to do that with my binary heap. Any questions? Yes? Okay, you're saying it's wasteful, but you're saying those pointers were wasteful. Why don't I use this instead? There's wasteful in a constant factor sense, and there is wasteful in a big O sense. Does everybody see that if you use explicit pointers, suppose I have an n-node tree, okay, and I use pointers, okay, how much space is it going to take to represent it? It's still going to be order n, right? I'm going to have, for every node is going to be my key field and 2 pointers. Those pointers you may say are wasteful, but it's only going to be a total of 3 times as much memory as it would have been if I didn't have to store the pointers. Do you agree with that? Now note that if you were given a horrible tree like this, if you explicitly stored it with pointers, it would still be, if you had n nodes, the space would still be order n, right? But if you stored it in a heap, okay, using this array-based tree, if I have a tree of height n, how many nodes in my array am I using? How much space in my array would I be using? Not n squared, 2 to the n. Okay? 2 to the n. Let's look at this. This is important to realize. Okay? You are using a space that is exponential in the number of elements, right? Notice what happened. My array I needed. To store 2 elements, I needed 3 elements in my array. To store 3 elements, I needed 7 elements, right? To store 4 elements, I needed 15 elements in my array, right? To store 1 extra element, I am doubling the size of my array. Do you see how I'm counting that? How many times, if I take a number and I double it n times, how much is that number? What is 1 when I double 1 n times? 2 to the n. Does everybody see it? It's 2 times 2 times 2. Any questions? So you've now got an exponential space data structure. That sounds wasteful, right? Multiplying it by a factor of 3 sounds like a bargain on this scale, right? That's why we worry about the big O notation complexity. That's where we get scared when we see something like this. Any questions? Note, by the way, while we've got your thinking like this, what's the relationship between n and 2 to the n is exactly the relationship between log n and n. Does everybody see that? Okay. If you have a tree of height log n, how many nodes did you have in it? 2, basically 2 to the log n or n, right? Here, if you had a tree of height n, how many nodes did you have? 2 to the n. So just as 2 to the n looks ghastly compared to n, it is just as ghastly to compare log n to n. Log n is a big, big improvement over n. It's an exponential improvement. That's why I get excited about logarithmic height things or logarithmic time things, because it's as big a win as going from exponential to linear to go from linear to logarithmic. Any questions? Okay? How many people see that? Okay, that's something you've got to feel the power of the logs. Any questions? Okay, good. Okay, so do people see that the array binary heap representation should be recognized as a cute thing? Okay? And in this case, it works out nicely if we don't need the full flexibility of our binary search, or a binary tree, where we need to use those pointers. Okay? Any questions? Okay, good. Let me come back. Boom, boom, boom. So let's think now how we could build this heap data structure. Here we have a heap. One way to build a heap, starting from nothing, is just like how did we build a binary tree from nothing? We had an operation called insert that, given a structure, would insert a new element into it. Building an empty tree was not hard. That was just a nil pointer to start with, right? And the key to building them was to have a fast insertion operation. Suppose I want to insert a new year into this data structure. Where would I have to insert it in order to keep my heap-shaped structure? Yes? It should be clear that if I want to keep my beautiful property, I want to insert my new element over here. Where is its parent going to be? 11th parent is going to be divided by 2 and take the floor, okay? Which turns out to be 5. So putting an element here is where I would want to put my next element I insert. Does everybody agree with that? Suppose the new year that I put in here happens to have been, let's say, the year of the Magna Carta. I think that was 1215, okay? And if anybody knows about the Magna Carta, but suppose we wanted to insert the year 1215 into our data structure. If we put it here, the shape of my heap is perfectly happy. But what is not happy? Okay? Yes? The parent node here is unhappy. Why is that node unhappy? Okay? It is because for every node it wants to be smaller than its children. Right? And that is not true now. So if I'm going to do an insertion operation, I'd like to now maintain it by fixing up this heap property. How can I fix the heap property? Okay, yes? Switch it with its parent if it's smaller than it. Okay? So she's suggesting that I take this thing, put a, let's see, I think I have another color here if I'm right. Put 1215 here, and make that 1865. My question, if I do that, is this element over here still going to be happy after the swap? Okay? This element?
It will always be happy because the parent has to be less than it. So if the other node is less than the parent, then the other node can be less than it.
The property this node had to be was less than its parent. If I am replacing its parent by an even smaller number, does everybody see that this node is happy? Okay? If I do that swap. This node is happy because it is now less than its parent. I explicitly did that swap. Can anybody be unhappy? Who can be unhappy? The parent of the other one. Parents are always unhappy. It's one thing that you sometimes find. Okay? So what is the basic idea here? In a constant one comparison, comparing me to my parent, which I could get at in constant time, I could decide whether I am less than my parent, swap myself, and I push the problem one level of management upstairs. Does everybody see that? And now I'm faced with the same problem. Is my parent unhappy? Yes. If so, let me swap, okay, me with my parent. Okay? Who is going to be unhappy? This guy's going to be equally happy because its parent has gotten smaller than it. So all of this subtree is going to be happy, right? Is this guy going to be happy? Well, in some sense, its parent has gotten bigger, right? Parent used to be 1215 and now it's 1783, right? But it was already underneath this as a grandchild, right? So this element had to be bigger than this element. So it is still going to be happy. And again, in constant time, I've pushed the problem one node upstairs. Does everybody see that? And so I can keep going up until the root. And at that point I will stop, because if this guy is less, when I put this guy here, it is the minimum element in the entire heap. It has become the root. Everybody is happy. Any questions about that? Any questions? How many people don't see how I have inserted this element in the heap to fix up my problem? Any questions about that? How many people get it? People don't get it. Okay? What should the running time be? The running time should be, I have, at each level, I am doing a constant amount of work. My heap is of height log n. Log n times 1 is log n. The total time for doing insertion was order log n. Any questions about that? Yes? Now, if I did this, how fast could I build a heap? If I have n elements in my heap, how fast could I build my heap? Doing it this way by repeated insertions, how long would that take? If each insertion took log n time, and I was doing n insertions, how much time does it take? Big O of n log n time. The question says, might there be a faster way to build a heap? Okay? And it turns out there is a faster way to build a heap. Okay? So, which I think I'm going to go through. Okay? But does everybody see why? The important thing here, before I get into anything even cuter. Okay? The important thing to see here is that I can insert a heap, okay, by basically doing this incremental construction, okay, and that it's going to take log n time per insertion, a total of n log n time to build the heap. Any questions? Actually, before I try to build a faster heap, let's look at actually, let's just look at this a little bit more before I get too carried away here. First, I encourage you to look at the code in my book and elsewhere about how simple this thing actually is to do the insertion what I did. You should, to make sure you really understand it. What am I going to do? I'm going to insert the element at the end. If it had n elements before, it now has n plus 1 elements. I write in the nth position my new element, and then I do my bubble up procedure. What is my bubble up procedure? My bubble up procedure is, as I happen to have implemented it, recursive, although you could have done it iteratively. But what am I doing? I compare me to my parent. If I am less than my parent, I am going to swap me with my parent. And then I'm going to continue my bubble up procedure from my parent stop. If I was not bigger than my parent, the job is done and I bomb out of this thing. Okay? If my parent is minus 1, that means I'm the root, right? If my parent is the null pointer or, whatever my symbol is for stopping, that's when I stop. Any questions about how I insert something in a heap? Okay, good. Let's look at deletion from a heap. Okay? How would if you look back to my my vision of doing selection and sort, okay? I wanted to constantly delete I wanted to find the smallest element, which you tell me was at the root, Okay? I'd also like to delete the smallest element. Okay? How can I go and delete the smallest element from a heap and still give me a heap? Okay? Any ideas? Okay, let's say you.
So you remove the root and then you reheapify.
So reheapify, I haven't talked about heapify. Let's think what I would do. Now let's do it without words. How can I now delete this element from a heap? Yes?
You would remove it and move the element that's at the last index into the first spot.
Okay. You're saying you want to move this guy in, okay, to spot. What does that guy have to do with anything? Okay, why do you want to move this guy?
Because then it will still keep the heap property where it's a log n.
Okay, so the advantage of taking this guy out to delete, taking the nth element and then replacing it by this, is that I can now delete this guy and my shape of my heap is right. If you're sitting far enough away, you can't read the numbers in the array or written on the tray. This looks like a well-balanced heap now, right? The shape is right. Okay? But what is the problem now? The problem is that the labels don't necessarily satisfy heap order. Does everybody see that? Any questions about that? So how can we fix this problem? How can we make this guy happy? Okay, yes? Swap it with one of its children. Which one of its children should we swap it with? We could look at its two children, this one and say, which is the smaller, me or of my children? The smallest one here happens to be 1776. What I should now do is put 1776 over on top, put this element 1941 down here, and now I have pushed the problem down lower. Does everybody see why is this side of the heap happy now? Okay, let's make sure that if I did that, I promoted this element up to the top. Why is it that every element in this part of the heap is still happy? Maybe this guy wanted to go to the top of the heap, okay? But it lost a direct comparison against its brother, right? Its brother was less than it, right? That's why the brother got to go to the top and it didn't, okay? It is still less than the root, and everybody else is unchanged. Does everybody see that? So this side of the heap is perfectly happy. Now, are we done yet? Well, in one step, or in a constant number of steps, looking at three elements, we push the problem down one level. And how do we know whether we are happy now, everybody's happy now or not? Yeah? Is it, compare it to its children, in this case 1941 is less than it. So in this case it is now happy. But if one of these years happened to be much lower than that, okay? Again, in a constant amount of time, we're going to push this element down a level, okay? And everybody will be happier, okay? Once it is happy, meaning it's bigger than, it's less than both of the children, the process stops. If not, it proceeds to a lower level. There are log n levels, each of which takes a constant time to move the element down. Deleting the minimum takes order log n time. Any questions about that? Does everybody see how that works? How many people get how we did deletion? How many people would like me to say it again? Anybody? No. Okay, that's good. Okay? So we can do insert and delete in constant time, in log n time. And in fact, this notion of taking the root element and percolating it down to its right position is a cute enough operation that we will call it, give it a name. The name of this thing is something called heapify. That's bubbling down, okay? And we will call that heapify. I may use that later on, depending on how much time there is at the end of class. Any questions? Okay, so we can insert and delete, insert in a heap in log n time, which means we can build the heap in n log n time. We can delete the minimum in log n time. That means that we can go do this heap sort algorithm, this selection sort algorithm, using a heap where it will be order n log n time. Okay? We will build a heap. How much time did it take to build the heap according to our method? By doing n insertions? N log n. Then what we're going to do is n times. We're going to pull the largest element out and readjust it. Each time we do that, that would be n times log n. N log n plus n log n is n log n. And so what we call heap sort is simply selection sort with a better data structure called a heap. Any questions about that? So this idea of a, a data structure where you are going to repeatedly insert elements and pull off the max, okay, or the minimum element, is an important data structure. We did it here with efficiently using a binary heap. We could have done it with a balanced binary search tree. There are other data structures that do it. The abstract data type that allows you to do, repeatedly find the min and, repeatedly find the min and do insertions, okay, is something we call a priority queue. And me as an algorithm designer, I think a lot about priority queues. Priority queues are an abstraction, okay? They're a data structure that only does three things, okay? They allow you to insert elements, they allow you to find the minimum, and they allow you to delete the minimum, okay? But this is a paradigm, a pattern, or an abstract type thing that's often enough, it's good to file in your head the idea that there is this thing called a priority queue, and think when something is modeled by a priority queue. Then you can use a heap, or you can use a balanced binary search tree, and get this good log n time behavior. Any questions? So what are things in life where you might use priority queues to model what is going on? I claim one example has to do with dating. Okay? How do people maintain the order of potential, the data structure of potential partners you can ask out on a date? Again, I understand dating patterns may have changed since I was doing these kind of things. But in base principle, what is the basic way that this should work? You know, every person, every potential dater should have a pool of candidates that they have met, that they have evaluated in some way. They have given them some kind of a score. You, 6.3. You, 1.9. You, nothing personally. You, 10 or something like that. You understand this principle, right? Who is the one that you want to ask out as a date next? Okay? In principle, it should be who? The person who's first in alphabetical order? No. It is the person who has the best score, the minimum bad ranking, or equivalently the maximum good ranking, right? So a priority queue supports exactly the operations you need to maintain your dating data structure. What is the goal? While it is Friday, so I can make plans for Saturday. Find the minimum element, the highest ranked individual. Call them for a date, correct? If I get turned down, what do I do? Okay? Delete this person, okay? And call the next man, right? I then have this date. What am I going to do after the date? I'm going to reevaluate them, correct? Maybe we had a good time, the score goes up. Maybe we didn't have a good time, score goes down, right? I am now going to want to delete this minimum and reinsert them with the new score. If I use a priority queue, okay, then I can maintain this data structure in log n time, despite the fact that I have n potential candidates to date. Any questions about that? Does everybody see that a priority queue is good for maintaining priorities? What is the most important job in an operating system to execute next? What is the most important person to ask out next? That is what a priority queue is good for. Any questions? You know, when I talk to students sometimes, they'll say, oh, can I represent this data in a list? A list is a weak word that doesn't tell you any properties you have. A priority queue says, I need to find the min, and I need to be able to insert things, okay? And that is, when you use those words, you know that you're thinking about the right thing. Any questions? What else can you use a priority queue for? Okay? There are a bunch of other things. It is often the case in simulations. You want to have a simulation where you have events that have to happen. You want to simulate what is going to happen in this big and complicated world. Okay? Somewhere along the line, you can predict that an event is going to happen at a particular time. Like, for example, we know that the next presidential inauguration is going to be January 20th, 2016, right? We can insert that into a priority queue. Maintaining a calendar is in some sense a priority queue, right? It's a bunch of events. If you want to go and do the events in your calendar, what are you always interested in? If you're rush busy, you're going from each event to the next event, right? To maintain your calendar, you want to always ask myself, what is my next event to do? That is find min. You want to say, oh, somebody wants to schedule an appointment with me? Insert that into my calendar. Insert that into my priority queue. Okay? If all you're going to be doing is inserting new tasks and executing them when the time comes, the right data structure for that is a priority queue. Does everybody get that? In some, well, the final example that I think I want to give here is that in some algorithms, you want to do something that is heuristics. A common heuristic is something called a greedy heuristic, where you always want to pick, let's say like in your homework problem, you said something about the fact that, that one of the homework problems here dealt with simulating bin packing. Finding, and what was the idea? They always wanted to find, I have a new item I want to insert. What is the bin with the most amount of room in it? Right? That was what I really wanted to do. If I had a data structure like a priority queue, I want to constantly say, what is the bin with the most amount of room? Using a priority queue, I could get that in constant time. I could insert my item into this bin. That would require me to delete the current bin from my priority queue, then reinsert it. Does everybody see that? The basic data structures that you would be doing, a priority queue is sort of the right way to think about it. And whenever you're doing something where you always say, do the best thing, do the best thing, do the best thing, a priority queue is a good representation for that kind of data structure. Any questions about that? Does everybody see how a priority queue is the right way to think about that bin packing problem? Okay? For the case of finding the worst fit, it's not the right way for finding the best fit. Okay? But if you think about it, priority queues are a useful paradigm. Think about it, make it part of your vocabulary, and we'll talk a little bit more about priority queues and how you use them next class. Thanks for your attention. Yeah.
There's a faster way to build a heap.
Okay, so one thing I said, okay, maybe not thanks for your attention. Some people are asking, hey, there's a faster way to build the heap. It turns out by being very, very clever, I guess I've got time to mention this. Sorry about this. It turns out that there is a way to build a heap in order n time, okay, by careful use of that heapify operation. Read it in the book and maybe we'll discuss it at the beginning of class next time. Maybe, okay? It's not big important, but it's actually kind of cute. Okay, thanks a lot.